This city, the people in it, in fact all life on Earth, we're only here by chance. We survived. 99% of all the species that ever existed didn't. They were wiped out in a series of global catastrophes, disasters that brought life to the verge of extinction. 4.5 billion years ago, the Earth collided with another planet. The impact nearly destroyed our world, but instead, it made it a home. This is the story of our planet's difficult birth. When I look around at all these people, it's hard to believe quite how lucky we are, because we're only all here by chance. Evolution wasn't an orderly progression from single cells to us. It was an imperfect, often violent process, and it's a miracle that we're here at all. In this series, we'll look at the theories about catastrophes that shaped our world and very nearly stopped evolution in its tracks. Like the time the planet was encased in ice for 25 million years, freezing the land and the oceans. Life survived, but only just. When huge volcanic eruptions poisoned the planet's atmosphere and pushed all life to the edge of extinction. Or the moment a 6-mile-wide asteroid smashed into the planet, killing 70% of life on Earth, including the dinosaurs. Even humans didn't escape unscathed. We might only have been around for a short while, but we've faced and survived supervolcanoes, ice ages, and even cosmic impacts. These catastrophes nearly wiped out life, but from their ashes, new species evolved. Without them, we might not be here at all. Tonight, we examine the first great catastrophe, the day our planet collided with another. The Earth's around 4.5 billion years old, so it's tough getting a handle on such an enormous amount of time. To put it in perspective, imagine the whole of Earth's history compressed into the 24 hours of a single day. Each minute on our clock represents around 3 million years. It starts ticking at midnight, and the first catastrophe was just minutes away. Our solar system hadn't even finished forming. 20 infant planets circled a new star, our sun. One of them was Earth. Its surface was a vision of hell, a barren, lifeless place shrouded in toxic volcanic gases. There was no water, no oxygen, and no moon. But this is all about to change. As our clock reaches 9 minutes past 12, that's 4.5 billion years ago, the Earth faces its first and greatest disaster, an impact of biblical proportions. Reconstructing Earth's early history is a major challenge. It's been obliterated and obscured by billions of years of erosion and volcanic activity. Astronomer Bill Hartmann has spent his life studying the events of the early solar system.
The record of the very first part of the Earth's history, all of that is wiped away on the Earth itself because we have erosion and rain and continental drift and continents colliding and mountains coming up and so on.
But all is not lost. There is a record of Earth's earliest days, just not on Earth. It turns out the best place to look is on nearby Mercury and Mars. their surfaces have barely changed in over 4 billion years, providing us with a unique record of events in the very earliest days of our solar system. They're dotted with ancient impact craters.
You start looking at those craters and you discover that there are not only 100-mile craters and 200-mile craters, there's 600-mile features. I mean, some very large objects.
These craters paint a picture of an intensely violent period, of a solar system littered with cosmic debris, where millions of asteroids and comets smashed into the young planets. In the thick of this all-out assault, the Earth too must have been struck.
It was a window into the early history of the Earth, and it made us realize that the Earth itself has had this tremendous history of impacts, enormous impacts that could have really damaged the whole planet. It got people thinking about what would be the effects of giant impacts on the Earth.
Hartmann realized that it wasn't just small asteroids hitting the planets. There were much larger objects too. And the larger the object, the more dramatic the consequences.
So the impact process, it's a wonderful kind of paradox. On the one hand, the small impacts tend to make everything the same, millions and millions of impacts averaged out, but the big impacts give individual personalities to the planets.
Take our planet, tilted on its axis at 23 degrees, with a nearby orbiting satellite, the Moon. We used to think that they'd been born together, until Hartmann proposed a radical theory. The Earth had been hit by something the size of another planet, creating that tilt and the Moon.
The key to our idea was that as the planets grew, you had the finished planets, but you still had leftover bodies. If one of those crashes into the Earth, just as the Earth has finished forming, that can blow out material from which the Moon could form in orbit around the Earth.
Picture the scene. The newly formed Earth hurtling round the Sun, and loads of other planets doing exactly the same thing. Including this one, Theia, about the size of Mars. It was orbiting the Sun at exactly the same distance as the Earth. The two planets were on a collision course. Theia hit the Earth at 25,000 miles per hour, with the force of billions of megaton bombs. The impact ripped off huge sections of the Earth's crust. Billions of tons of debris blasted into space. A ring of red-hot dust and rock formed around the Earth. Over the next 100 years, the rocks and dust slowly clumped together into a ball 1/50th the size of Earth. We call it the Moon. When Hartmann suggested the idea in the 1960s, people found it hard to accept.
Scientists were thinking of everything in terms of slow geologic processes, one grain of sand at a time, wearing down mountains. To think of something as colossal as the Moon forming as a result of a single event was hard for people to swallow.
But then Hartmann got the first real clue that his theory might be true. The Apollo project.
That's one small step for man, one giant leap for mankind.
American astronauts made 6 visits to the moon. They explored its surface, drove around its craters, and brought back 840 pounds of moon rock. For the first time, scientists could find out what the moon was actually made of. The lunar samples had a remarkably similar chemistry to the outermost layer of the Earth's crust. To most researchers, it was an interesting discovery. But to Hartmann, it was vital new evidence.
So you have crustal rocks, you have rocks on the surface, and a big impact comes in and blows all those crustal rocks away. And that material goes into space and forms the moon.
But many scientists were still skeptical. They just couldn't see how a massive impact could create the moon and the Earth as they are today.
I actually had people telling me we should exhaust every other theory first because this was such an outlandish idea.
It was a chance meeting at a conference with astrophysicist Robin Canup that gave Hartmann the breakthrough he was looking for. She was using computer models to study Saturn's moons.
Bill Hartmann came up to me after my talk and asked me, have you ever thought about applying your models about how moons form within and near Saturn's rings to the origin of the moon? And I said no.
So she tried it. Canup used modelling software to recreate the early solar system. Then she plotted a planetary collision of the kind Hartmann was suggesting.
So we're 4.5 billion years ago at the end of the Earth's formation. And we're in space and we're watching as a small planet, the planet on the right, is about to hit the young Earth, represented by the larger planet on the left. The collision takes place, and as we see it hits in a glancing blow. And you can see the impactor is completely destroyed by the collision.
Thea, the impactor, is annihilated. Earth survives, but only just.
Now this collision is incredibly violent, so violent that there's enough energy to completely melt the Earth. And in fact, at the end of this impact, the Earth is surrounded by an atmosphere of vaporized rock.
Trillions of tons of debris blast out into space.
Here we see part of the impacting planet sheared out into this long arm of material that produces a disk that we're seeing almost edge on in this view. And it's from that disk that the moon later coalesces.
Canup's model demonstrates that the moon was probably made of debris from both Thea and Earth. It explains why those moon rocks were so similar to rocks from the Earth's crust.
So I actually called my colleague and said, you're not going to believe this, but I tried this Mars-sized impactor case with about a 45-degree impact angle, and everything worked. And he said, you better check it again. And so I did check it again and did many more of these simulations, and sure enough, that type of impact is the one that gives us the Earth-Moon system today.
Canup's work was further evidence that Hartmann's radical theory might just be right.
So it was very exciting as Robin did her models and they started to say, yes, there can be moon-forming debris left in orbit around the Earth, and the moon would form from that debris.
Hartmann and Canup's work showed that our moon was created by a violent cataclysmic collision between Earth and its twin Thea. The Earth narrowly survived complete destruction, but the collision triggered a series of events that transformed our planet. It became a climate hellhole with extreme weather conditions and giant tides. But bizarrely, those deadly conditions created the building blocks for life itself to evolve. On our clock, only 10 minutes have passed. That's 30 million years in real time. It was the single most important period in the Earth's history, a time of incredible violence that saw the creation of a new Earth and our moon. The massive impact which created the moon very nearly destroyed our planet. But out of this catastrophe came a new beginning, because the impact set in motion a chain of events that transformed the Earth from a vision of hell to the blue-green oasis we call home. Scientists set out to reconstruct those events, starting with the moments immediately after the impact. Ithaca, upstate New York. Paleontologist Judith Nagel-Myers hunts for clues that might reveal what happened to Earth just after it was struck. No evidence remains on Earth from the time of the collision, so scientists are constantly searching for ingenious ways to look back in time. Nagel-Myers uses fossilized corals. These ones are just 400 million years old. But they hold a vital clue to what conditions were like on Earth 4.5 billion years ago.
Personally love about fossils that you find them and they open up a window in time. Just by looking at their remains and their skeletons, you can reconstruct the environment that was here before, long before humans are even on the Earth.
The coral fossils have an unusual property that allows them to capture a day-by-day snapshot of conditions on early Earth. They lay down layers of limestone, a new layer for every day of the year. You can see the same process in every reef, including today's coral.
If you actually look closely at these modern corals, you can see tiny lines that they built while they're growing. They're kind of similar like growth rings on trees. We know nowadays that one of these lines represents a day.
The daily growth layers build up to create a larger annual ring.
If you count these daily growth rings, you can actually, in modern corals, count 365 growth lines per year.
But the 400 million year old fossilized corals don't have 365 growth lines per year. They have 410. When these corals were alive in the ancient oceans 400 million years ago, the world was very different. A year didn't last 365 days, it lasted 410. But whether you measure it in days or hours, the Earth's orbit around the Sun always takes the same amount of time. A year is always constant. The only explanation for more days in a year has to be that millions of years ago, each day was shorter.
That means that back in the day when this animal was actually living in the ocean, that the days had less hours than they have today.
400 million years ago, a day lasted just 21 hours. And if days were shorter, then the Earth must have been spinning faster. Calculate back from 400 million years ago to 4.5 billion years ago, just after the huge collision, and each day would have lasted just 6 hours. And that means the Earth must have been spinning much faster than it does today. It seems the massive impact that created our moon also set the Earth spinning like a top. It was the first step towards the habitable Earth we live on today. But you'd never know it. The rapid rotation unleashed the worst weather the planet has ever seen. It looked as though the collision with Theia had left the Earth an uninhabitable world. At 12 minutes past midnight on our clock, 40 million years after the Earth first formed, frozen comets started smashing in from space. It was a savage bombardment, but it wasn't a disaster. In fact, it was a blessing. The icy comets melted, helping to create the first oceans. But the young Earth was still a violent, hostile place. Its rapid rotation whipped up 500-mile-an-hour hurricanes. Rain and storm-force winds scoured the planet's surface. And the atmosphere was a lethal cocktail of carbon dioxide and acid rain. It seemed that there was no way life could ever have got started. Were it not for one thing. When the moon rose 4 billion years ago, it wasn't the familiar moon we see today. It was 10 times closer to the Earth and dominated the horizon. Its proximity was another consequence of that huge collision. One that led directly to the emergence of life on Earth. Because the moon was so much closer than today, its gravitational pull on the Earth was much stronger. It pulled hard on the Earth's newly formed oceans. The result, huge tides that ripped across the planet at hundreds of miles an hour. You might think these made it tough for life to get going, but you'd be wrong. This is the Bay of Fundy, Canada. It has the highest tidal range on the planet. And that makes it the closest we can get today to the colossal tides of early Earth. Physicist Neil Cummins is here to study what happens when the tide comes in today, and what that can tell us about tides in our planet's distant past.
What I would expect to see here is a huge wave, maybe 5-6 feet high, called a tidal bore.
He's waiting for the tidal bore to surge in at high tide so he can see at first hand the kind of forces that shaped the ancient landscape and created the conditions for life to begin.
Right up here, actually, in the middle of the channel, you can start to see the tidal bore. You can see the wave curling over.
Yep.
See the white water.
It's absolutely fascinating. Sounds like
you can actually start to hear it a little bit.
You have a feeling that there's an action here that you don't see anywhere else.
Should we go and meet it?
As the incoming tide surges upriver, it meets the outgoing tide, creating one of the world's largest tidal bores. The rushing waters smash into the edge of the bay. They rip sand, minerals and other material away from the shore and carry them out to sea. Fundy's tidal bore replicates in miniature the tides on the early Earth.
The ancient tides would have been at least 1,000 times higher. There's a tremendous amount of power in these tides, but nothing compared to what it was. This bore is traveling about 12 kilometers an hour. The ancient tides would have been traveling on the order of 100 to 300 miles an hour. And they would have gone much farther inland, much faster, and would have done much more damage.
"4 billion years ago, when the moon was much closer, the tides would have smashed inland at hundreds of miles an hour. Each tide churned up millions of tons of debris. When it retreated, it left a devastated coastline. The young planet Earth was being devoured by its oceans. And for us, that was good news. Because what the tides stripped from the land, they gave to the ocean, creating the perfect environment for life to emerge.
To get life started, you need a huge amount of minerals in the oceans that are free to mix and interact. The only way that the Earth could have gotten that was from the huge tides that the Moon gave when it was much, much closer.
The tides ripped minerals and nutrients from the land and mixed them into the oceans, creating a primordial soup. Scientists think that chemical interactions in that soup created the very first amino acids and basic proteins, the building blocks of life. From these ingredients, the first primitive cells would eventually emerge. Life that might never have developed were it not for the tides. Tides created by the Moon, a moon born out of catastrophe. A disaster that nearly destroyed the Earth, but without which life might never have evolved. But the Earth was still a brutal place. The planet was spinning wildly. The climate was too chaotic and the seas too brutal for single-celled organisms to evolve. But beneath those churning seas, a vital concoction was brewing. A few simple strings of molecules were assembling, and those molecules would be the precursors of life. It's 3:20 on our clock of the Earth's history. It's 500 million years since the impact that created the planet and its moon. Thanks to the moon's violent tides, the first building blocks of life have been created deep in the ocean. But the tides are too violent to allow the organisms to evolve. Something must have happened to calm the planet and allow life to take the next step. Otherwise, we simply wouldn't be here. This is KwaZulu-Natal in South Africa. For paleontologist Nora Nofka, this ancient gorge is a truly remarkable place. Here, she discovered fossils of some of the earliest forms of life on the planet. 3 billion years ago, this landscape was an ancient sea teeming with single-celled bacteria. A billion years after the catastrophe that nearly destroyed our planet, life on Earth was in full bloom.
It was really one of the great moments in my career. We were searching for fossils the whole day long, and then in the late afternoon, when the sun was shining in the right angle, suddenly we saw the fossils popping out everywhere, and it was just unbelievable.
The fossils were the remains of vast colonies of bacteria that grew as mats in shallow oceans. And they were some of the earliest living cells to inhabit the planet. There are bacteria very similar to these still alive today.
Those are living bacterial colonies. We term them microbial mats, and you can easily see why. Those mats look like little greenish carpets. They occur today everywhere, the sandy beaches.
The similarities between ancient and modern are striking.
You can see the rock surface is greenish colored, just as the living microbial mat as well. You follow my finger now, I show you the edge of the fossil microbial mat here. And here you see the sand underneath is such a microbial mat like this piece here, but it's fossilized and it's 3 billion years old.
The rocks all over the gorge reveal an astonishing diversity of ancient microbial communities. Ecosystems of bacteria as complex then as they are today. But the rocks reveal something else. They show not only when cellular life took hold, but how it was able to do so. Because when life emerged, it wasn't in the violent oceans left behind by the collision with Thea. It was in calm, shallow water.
Came first here into this outcrop, into the side. I saw all those different ripple marks, and they look just as they do nowadays. If you walk along a beach, you can see the same structures in the sand. So the preservation of those structures is just outstanding here.
It looks as though the tide has just gone out. Except these ripples are 3 billion years old, the fossilized record of an ancient ocean gently lapping the shore. With no sign of giant tides or hurricane winds.
The site shows that at least 3 billion years ago, the living conditions were normal. This is a peaceful environment here, so life could evolve.
Something had changed the planet's climate, making it hospitable for life. And once again, that something was the moon and its effect on the oceans.
The tides, since they've started forming, have acted as a brake to slow the Earth's spin. You can almost think of it as the brakes on a car, pressing on the tire and causing the two to slow down together. That's what's happening and has happened from the tides.
It's a process called tidal friction.
When the tides and the continents meet, the water pushing against the land creates friction. And that friction is literally slowing the Earth down.
Gradually, over millions of years, the Earth began to spin more slowly. As a result, the days became longer and the hurricane winds subsided. It was a step in the right direction, but on its own, it wasn't enough to create the calm seas we saw fossilized in KwaZulu-Natal. The moon was still close to the Earth, its gravitational pull on the oceans still strong. For the oceans to have calmed to a gentle ripple, something major must have happened. And the answer to what did was discovered in NASA's Apollo program, the final leg of man's mission to the moon. The McDonald Observatory, USA. Here, 40 years after man first landed on the moon, the Apollo mission is still going strong. Every day, NASA engineer Jerry Wyant rides up to his laser telescope in this remote part of Texas. His mission: to measure the moon's distance from Earth.
We're the last living piece of the Apollo project. And most of the public thinks that, oh, the Apollo project's they're dead and gone. And so they're surprised when I tell them what I do, I send a laser to the moon.
When astronauts landed on the moon, they left behind the American flag and something else: reflectors. Almost daily, Jerry Wyant and his colleague aim their laser at one of the lunar reflectors. They're measuring the precise distance between the moon and the Earth.
This is a 1 billion watt laser. We direct it at the reflector on the moon, and we measure how long it takes for this light to go from here to the moon and back, and that's our data.
The laser measures the time it takes light to bounce back from the moon to a trillionth of a second. But first, they've got to find the reflector.
Each panel is about the size of this map right here. So if you think about it, we're trying to hit something this size about 240,000 miles away. It's not easy.
They need a clear night, then they need to locate the target.
Yeah, they all look alike, don't they?
Yeah, so it's easy to get lost.
It can take up to 4 hours just to find the reflector.
Well, that right there, that would be the reflector on the moon, right there.
Tonight, the laser beam takes 2.3967 seconds to travel to the moon and back.
When I see the moon in the sky, instead of thinking romantic thoughts, I think, gee, I hope the laser is working okay.
It may not be romantic, but it is amazing, because each year Wyant's laser beam takes a little longer to bounce back. That means each year the moon's a little further away.
One of the reasons that scientists want our data is to confirm their suspicion that the moon really is moving away from the Earth. And they've used our data to report back to us the value of that. In fact, is yes, it really is.
The moon is spinning away from us at 3.4 centimeters per year. And it's this that holds the key to understanding why the oceans calmed and life emerged. 3.5 billion years ago, the moon was only 15,000 miles from Earth, resulting in mountainous tides. But bizarrely, these tides were pushing the moon away. They were so huge, they had a gravitational pull of their own, and that began to affect the moon that had created them.
The gravity from the water is acting back on the moon, which raised the water up in the first place. And this water is pulling the moon forward, giving the moon energy.
As the Earth span, it slung the moon further away, like an athlete throwing the hammer.
You can think of the Earth-Moon system as waltzing together. As the moon creates the tides on Earth, the Earth is slowing down, and the tides are causing the moon to gain energy and spiral away. The two have been doing this dance for 4.5 billion years.
So the catastrophe that nearly ripped our planet apart before life even started actually ended up making life possible. Violent tides filled the sea with vital chemicals. Then the Earth's spin slowed and the moon drifted away. The nutrient-rich seas calmed and life got started. But this new flourishing life was about to face another catastrophe, a disaster that would wipe out much of life on the planet, but without which we probably wouldn't be here. Some bacteria began to release a deadly poisonous gas called oxygen. It's 8:10 a.m. on our planetary clock, just over 1.5 billion years since the Earth was born. The first third of the Earth's life was violent, chaotic, and lifeless. Then the climate stabilized and life began to take hold under the seas. But suddenly, some bacteria underwent a change that would affect all life on Earth. It wiped out many species, but without it, no complex life, none of this, would be here at all. This barren landscape is the high desert in northern Mexico. It's one of the only places in the world where we can get a glimpse of what the Earth might have been like 3 billion years ago. Biologist Janet Seifert studies the bacteria that live in these pools. They give her a unique insight into how ancient bacteria changed the Earth forever.
You can walk out to the pools and you can see evidence of microbial communities with the naked eye. Now that's very similar to what early Earth was like. Early Earth was certainly dominated by bacteria. There were no large animals or plants. So we can use this as a proxy for early Earth.
These odd-looking lumps are particularly interesting.
So this is actually quite remarkable. I know it doesn't look remarkable. This looks like just a rock found in the bottom of this little river here, but this is actually a complex community of microbial life.
These lumps are called stromatolites. They're made of bacteria that deposit limestone, building up to form these mini reefs. It was organisms almost identical to these that populated the early Earth. These fossilised stromatolites in the Flinders Ranges in southern Australia are 3 billion years old. There's virtually no difference between these and the living structures Seifert's studying in Mexico today. Each stromatolite contains millions of blue-green organisms called cyanobacteria. And 3 billion years ago, their ancestors evolved an ingenious means of obtaining energy.
One branch of bacteria actually learned how to do one thing. They just used the sunlight for energy, but as it turned out, when they did that, they did it in such a way that they could split water and create and give off as a byproduct something they didn't want, oxygen.
These ancient microscopic cyanobacteria evolved a chemical process called photosynthesis. It converts light into chemical energy, with oxygen as a byproduct. It was a biological revolution, and it changed the planet forever. Cyanobacteria pumped oxygen into the oceans, then the atmosphere. Without cyanobacteria, we could never have evolved. It's thanks to them that we breathe oxygen today. If they hadn't invented photosynthesis around 3 billion years ago, there'd be almost no oxygen in today's atmosphere.
Once the cyanobacteria figured out how to produce oxygen as a byproduct, it changed our planet forever. It changed the way biology was going to evolve, and it changed the atmosphere completely.
It's a process that continues today.
I remember the first time I was swimming around down here, and you could see the small little bubbles accumulating underneath the ledge of the stromatolite. It was quite amazing to think that that process that we were actually visualizing in that way is what's creating the atmosphere today.
And those ancient cyanobacteria are the ancestors of every plant in the world today. Photosynthesis was incredibly successful. The bacteria flourished and evolved.
We always think about microbes being something bad and giving you strep throat. But if bacteria hadn't been able to harness the sun and then as a byproduct produce oxygen, you and I probably wouldn't be here now, because it's what allowed complex animal evolution to occur.
There was just one problem. 3 billion years ago, oxygen was bad news.
When it first happened, that byproduct oxygen was poison to most of the life on the planet. So it was a devastating thing that happened. All of life had to actually acclimate to the fact that there was oxygen in the atmosphere.
But a few bacteria did learn how to handle it, and it's those ones that led to things like us.
Actually, I feel pretty lucky, because that bad poisonous gas that cyanobacteria had as a byproduct, if it hadn't accumulated in the atmosphere, then I wouldn't be here. So as far as one of the major biological innovations that happened in 3.8 billion years, it has to be up at the top of the list of one of the best ones for us as humans.
By 8:12 in the morning on our clock, the atmosphere had oxygen and the oceans were teeming with bacteria. Evolution, life, had begun, and it all started with a catastrophe. That impact is the only reason life ever evolved. But if it had been even slightly different, there might be no one here at all.
If you consider all the different types of impacts that could have happened and have left Earth-Moon systems that weren't nearly as habitable as our own, it's really quite something to think that we got lucky in a sense.
And that's the point. We did get lucky, not just with that first impact, but in countless ways over billions of years.
What we're realizing now is that catastrophes have played a much larger role in the evolution of life on Earth than anybody believed earlier. You have to realize that we are at the end of this long chain of unique events. Had they played out differently, this guy wouldn't be sitting on this rock here.
There's only one conclusion. We're not here because we did something right. We're here because we're lucky. The collision with Thea was just the first of many random rolls of the dice.
It really makes you think about this completely unique sequence of random events that were all necessary to give us the Earth we know today. And if any one had just been a little different, the whole world around us would be different. We wouldn't even be here. It gives you an appreciation that a catastrophe is always, in some respects, a beginning.
The collision was the beginning of a new Earth. It set Earth apart from all the other planets in the known universe and started us off on the long and difficult journey to life as we know it. And without it, this city, the people in it, you, me, we probably wouldn't be here at all. On the next episode of Catastrophe, Earth freezes over. Life had just got going, and then the planet's surface turns to ice and forms a snowball Earth.